Hi everyone, I am Stavros, and in this session we are going to see how language models are working. Why this video differs from other videos out of the internet is because here we are trying to see the deep internals of language models, how are constructed, what components are used in order to make it work. And of course, this is a tiny implementation that can run in a single machine, even on your personal laptop. So basically you can run this repository in your PC using your CPU cores, or if you have a virtual card, you can run it even in your GPU. So let's get started. The repository is called TheLittleBaby, and it's under my name, Kourea Stavros, into the GitHub. This repository contains some folders containing practically some data for the input of the model, some output of experimentations, and the actual source code of the implementation. Also, we have a second repository called again TheLittleBaby under my name into the Kanji phase, but this time we have a different set of folders, and here we keep the pre-trained models, the weights, biases, practically the parameters of the models, the tokenizers, the vocabulary that is used to tokenize the dataset, and the configuration of during the execution. So practically, you can use them only if you want to make an inference based on pre-trained model or fine-tune an already pre-trained model. Otherwise, these are not mandatory. Let's see how it works. First, we clone this repository or we download the zip and we extract this zip into our hard drive. As I said, optionally, we can download all this repository with these folders and put them in the same directory. So practically, we will end up in the structure like this, both folders from the GitHub and folders from the Kanji phase. Then we can open this using the VS Code, and the only thing that we're going to need is a Python kernel version after Python 3. It's okay because this implementation does not use any library. We are using only Numpy if we are going to use our CPU, or CuPy if we are going to use our GPU. So every function is implemented from scratch, and we have a great visibility to see how each line of code works and how make importance into this code for the model. First of all, let's see some high-level details of this repository. First of all, we have the input folder. This folder contains two datasets, the Shakespeare dataset and the Sophocles dataset. We can see in the README file the definition of these two datasets. For example, we see that given the Shakespeare dataset, we have 32K paragraphs or 35K of sentences or 202 words, and at the end we have 1 million characters. In this implementation, we have chosen to make the ability to change the infrastructure of the model, practically the skeleton of the model, based on some switches. In this case, based on tokenizer, we can assume that a token is a character or a word, or in the modern models, a character or a set of characters is a token, the byte per encoding. So in this case, we are going to use character tokenizer. So we're about to train and test models near to 1 million tokens of training. Given this information, we can also start using this Python GPT notebook file from this directory, and we are going to explain each cells one by one. So let's get started with execution. The first thing that a notebook will ask is where these folders are in perspective of the location of the notebook. So we see that the notebook is in the same level with the folders. That's why we are going to say same level. This is just for flexibility if we would like the Python file, the notebook file, to be in another directory rather these folders. And then it asks us about a specific operation. We would like to train the model, we would like to fine tune or inference or delete or give and provide info for already pre-trained model. So before I started, let's see first the cells of this notebook. The first cell is a simple cell that is telling to the Python kernel to reload the modules that belonging to source. This is only for your convenience in order every time that you make a change to instantly uncache the previous code and be able to always execute the latest modification that you have done. So here we see the list of that all of these modules are reloaded again. Then these are the inputs for runtime path and runtime plan that we show previously when we execute the notebook. Then we define the paths that we explained like the input folder which giving the dataset. And of course, there are other folders like the settings, and the settings is a special folder used on during the training. For example, in the current here, we can see the definition that we can play among different hyperparameters that we will explain some of this video and some others in deep detail in other series. So after that, we have the config file, which is practically a snapshot of the settings file given the GUID execution of the model that contains the information of the hyperparameters like it was at the moment the model trained. We have the tokenizer, which is practically, again, a snapshot of the vocabulary that is used to transform the characters to tokens and the tokens back to characters again. We see that in this particular tokenizer, every character is English character because it's trained only on an English dataset of Shakespeare. Then we have the actual model definition, which is under the models table. And this is again a JSON file that can give us flexibility on weights and biases of each particular object inside the model. Then we have the outputs. The outputs is a folder that keeps first two types of JSON. One is the report. The report is the information of the model process of training. So here we have information like how much time does it take for a batch process, or how much time does it take for a full epoch. And also we have some other metrics and KPIs. Finally, at the end, we have the completion file, which is practically the output of the model. Here we see how much time it took for a simple completion, and if we used cache, KV cache or not, that we will explain, of course, in another video. If we have gave any prompt during this, or the model generated free and continue practically the trained dataset. So I will start the Python notebook again and start see what happens. So we will select same and then train. Then after the reload and the inputs that we provided and the paths that we have defined, what is happening practically is that in the next cell we import the actual code of the GPT language model. And of course some runtime functions to get information from files and also to store some information to files. The first cell now that we see below is the train cell. Here we have a specific sequence of operations which are very simple. First of all, we load the input file, the dataset. We load the current JSON file that we just explored with the hyperparameters, and we load this config file. For the training, we will say that we are not going to give any prompt, so we will let at the end the model produce itself some output for us, and the max token is none, which fallbacks to 500 tokens. Then we save this just for our convenience to a last .json file in order to be easy to reuse the same configuration if we would like. Then what we do is that we load the model into the memory. This is an empty model without any parameter, a learn parameter. And then we load from the config file for important parameters: the number of epochs, the batch size, the learning rate, and if we would like to warm up the optimizer. And then we start training the model given this train function and all these inputs that we defined above. After the training is complete, the next thing that will happen is that we are going to save the config snapshot we explained earlier. We are going to save the tokenizer. We are going to save the model itself with weights and biases called parameters. And finally, the report with information of the training process. We will do an inference based on non-prompt. And finally, we will store this completion in a separate file. So it's a specific order of things. As you can imagine, the next cell is the fine-tune option. The fine-tune option uh, follows exactly the same order with just one simple change. So first of all, it asks to give a GUID of pre-trained model because you need an already pre-trained model to either do a new training even on the same dataset, just a different epoch, or a completely different dataset, let's say a Greek dataset like Sophocles. And then the model will be able to produce text even in Greek, even in English. So after we again load the input file, we save the last settings, we load the config file, we load the empty GPT model. What we do this time is that we load the pre-trained model from the given GUID. And then we start doing exactly the same process. Uh, of course, we are going to load the tokenizer that it is used for the previous training. And then again, we export these parameters, the epoch, batch size, learn rate, and the warm up. And we do the train and we save exactly the same things, but with the suffix of fine-tuned in order to be able to compare between the fine-tuned and not fine-tuned. So the third cell is the inference. The inference is going to use only the GUID of the model and is going to load again the settings. And this time, the only thing that we will do here is just load the GPT file, load the model from the JSON file, and then do a simple inference. Then the delete shell, the for shell, is only to delete a pre-trained model that we no longer need. So given a GUID again, we are going to delete all these files from these particular folders: the config, the tokenizer, the model, the report, the completion, and the chart that we are going to discuss later. The info given a GUID of the model is going just to display the information of a particular model, like the config snapshot, in order not to manually go through the repository, find the config file and open it with a notepad. Is going just to print it for you with some other information like the flops calculation. So now the last cell is the actual flow that we will define if we need cache or not, that we'll explain in another video. And given your selected plan is going to perform this process. For now, we have selected the train, and because the current file has the CPU selected for the option device, we see that the notebook is using our CPU with 16 cores. Currently in my laptop, I have an i7 Intel 13th generation of CPU. We see some information of the model that we have in the current file, and we see that the process is started. So what is happening here is that the model is splitting our text in batches. In this case, the batch that we have selected is 16. That means that 16 arrays will be used at the same time to process the model in parallel. So this is also the throughput that is used in order to utilize your CPU and memory, or your GPU and GPU memory if you have selected GPU for option device. Then what is happening practically, the number of context is how many tokens we would like the model to learn in a sequence. So practically when you have selected the number of contexts 128 and batch size 16, it means that 16 of this 128 array of characters will pass through the model in each step. So that means that there should be a relation between the how much processing power and memory does it takes to process the model based on these parameters. And in order to identify that, a good point of reference is the README file, and all of these parameters are well explained here. For example, if we look under the context size, we will see that directly increases the size of positional embedding table. So at the end increases the model size, and of course has a major impact on speed and the performance of the model. So the process of training will take, of course, much longer. There are a few parameters that have almost a linear relationship between speed and the size of the model. For example, the layers is the ability of the model, the capacity of the model that has for knowledge. All of these parameters we can explain it, of course, in the next video, because this is a high level video explanation of how this language model repository works. And if we know very well how the language model works, or if we don't know at all, we can see from the documentation folder a specific, not from documentation, but there is another folder called material, which has a good diagram like this. So if we make a full screen, we can see that in the left we have this diagram that represents the actual model process. So what is happening practically is that we give an input to the model, the tokenizer based on the selection. If we are talking about a character tokenizer or word tokenizer, we'll split the characters or the words, and then we'll pass it to the next layer that we're going to transform in this stage each token to a vector into the multidimensional space, and we will take the position of each embedding. We will pass it to the block. The block is what we discussed earlier, the complex phase that will make all the magic for us. So the block consists from two parts. One is the attention mechanism that is going to give the model the knowledge, practically is going to calculate how much each token contributes to the next probability of each token to be generated. So practically tries to understand how each character or word is related together in a sequence. So in the middle, we see that we have two type of attentions. Of course, we don't use both attentions together. This repository has the ability to make you choose, to let you choose which attention mechanism you want. So for example, here we have the MHA, which stands for multi-head attention, or MOH, different implementation with different steps. And of course, we have different options for networks. We have the MLP, which stands for multi-layer perceptron, and we have also the MOE, a new modern technique. Uh, these are not the only implementations that we have in the model. This is just for demonstration to understand that you can choose, play with, observe what is inside and how all the things are working. If we switch back and we go to the source, which is the actual source code of this GPT model, we can see that we have one folder attentions, and here we have 7 different attention options that we can choose. And of course, if we go to MHA, we can see all the code is used in order to make all this magic happens. And here, of course, because we don't use frameworks like Torch and we use only pure code of Python, we have to implement everything from scratch. So we have the forward step, and of course, we have the backward step that will calculate the derivatives in order to give the information to optimizer to know if this step was good or not and which parameters was better and which weights and biases which better and affect the model well or not. Same happens with a network. We have a folder called network, and here we have again 7 implementations of the networks. Each different attention and network is, of course, documented in public white papers, and you can have them as a point of reference. Then, after you have selected in your current file JSON the proper attention mechanisms and the MLP, and of course the other hyperparameters, all these are going to be used in this language model. So this will take much time, maybe hours, maybe days, maybe weeks, depending on the selected device, CPU or GPU, and of course the configuration. Another thing to have in mind is that there is a special parameter that affects linearly the time that is needed and for the model to be trained, and is the epochs. So the epochs is how many times the model will process the same content in order to learn better uh, the, the given input. And of course, there is the number of layers, that it's the capacity of the model, how many blocks are there. So every time that you multiply by 2, this means that it will take almost linearly the double time, and it will consume double of your RAM and CPU power, or same if you have selected GPU. So if you have selected very high number of context and embedding and number of layers, it might be the case that doesn't fit into your RAM or in your GPU memory, and it will throw an error. That means that you can have a lower value divided by 2 always to make it fit in your workstation. Of course, another parameter which is very important is the batch size. The batch size does not affect the quality of the output, but affects the throughput that is needed in order to process the model. So in this case, you can play with this parameter in order to make it fit to your machine. But of course, this will take much time. Then, assuming that this is completed, we are going to interrupt this and we'll clear the output. This time, what we'll do is the following. We will go to README and we will find an already pre-trained model. For example, we can use either from this table that run using a CPU, either from this table that run using the GPU. Now, this time, let's take one from the GPU. So in this table, we have also give information on which GPU or CPU we have trained the model, because each GPU or CPU cores have different processing power, in which dataset, and then we have documented all the options which are used at the moment of training. For example, here we see that we used the character tokenizer. Each token is considered as a character. We used the pre phase for the block that we will explain in a different video. MHA, multi-head attention, and multi-layer perceptron for the network, and the parameters for the context size, the embedding size, the dropout, head size, number of layers, etc. At the end, we can see a high-level overview of how much time each batch took, how much time a full epoch took for each model, the quality that evaluated by a bigger language model like GPT-5 nowadays, the size in bytes of the model, the parameter count, and the model ID. So let's see how this table is working. Let's find first a good pre-trained model with a good quality. So if we look this value here of the quality, we see 60, for example, for this GUID. Let's take not the fine-tuned that we will explain just now. So this GUID starts with 5E. If we look the 5E into the folders, we are going definitely to find the 5E here. So this is the simple 5E, not the fine-tuned, and we see that this model was trained truly with GPU. We see the model of the GPU, we see the parameter count, and all the things that was selected during this training phase. So here we see a different attention mechanism and network mechanism. Of course, apart from that, we have the model itself that is residing here, and we can observe it because it's a JSON format, and this gives us a great visibility over its weights biases, which is called parameters. And this is a huge file, contains all the layers and each block of this model. Then we have the tokenizer. Again, we have the same thing, 5e, and this is practically the vocabulary. Here we see Greek letters because we trained it on Sophocles Greek dataset, and this is a Greek dataset, so we see Greek characters. This is a mapping between the character and token embedding back to token character. Apart from that, we have the output folder that practically contains two types of objects, the report. So the report looks like this, contains more information about each batch, how much time does it took, and the training loss during the batches. A great thing here is that we can observe that the training loss is getting decreased in each step. And this is good because we know that the model is actually learning something. And we see that it starts decreasing and decreasing. We have the average time per batch, the average time of training and validation batch, and we have also the time per epoch and the average time per epoch. Finally, we have the completion file that this model, the 5e, generated during the inference after the training. So we see a Greek text that almost makes sense depending on, of course, the hyperparameters that we selected during the training. So now let's see how we can use this pre-trained model to make an inference. We run again the notebook, we select the same, and then we select inference. Now it will ask to which model do we need to make the inference. So we select this GUID, and then the next question will be what prompt do you want to provide in order the model continue from there. We can select none and let the model be free and continue based on probabilities what he thinks will be the next token. And how much tokens we can select 128 tokens, and then it will run on GPU because the configuration of this 5V was on GPU. Of course, it doesn't matter if the model was trained on CPU, you can inference on GPU or the opposite one. So now we see the generation happened and we have a new Greek text that almost makes sense. Practically, this is how it works. And now, if we would like to observe better what is happening internally, we can expand this folder of source, and the major file that contains all the skeletons is the GPT Python file. And here we can see that all the imports are coming again from the same folder because every implementation is written from scratch. So practically we have the linear layer, we have the embedding layer, the normalization, we have the tokenizer, the optimizer, and the big block that we just discussed. So if you right click here and go to definition, you can see the block. Now we are navigated into the block Python file, and then here we can see how each layer is connected, and then we can see the feed forward step, how it's connected each other. So here in the upper, we can see that we have a self-attention layer and we call it from a class attention. Same happens for a network. If we go inside, we can see that depending on our selection is going to use a different class, so a different implementation. And if you would like to go deeper, for example, to see how multi-head attention works, you can go and select the definition again and see that this is uh, contained from all the known query key and values, vectors, and how the dropout works on these projections and how the feed forward connects all the dots together. So every step here has an opposite step. So for example, this is the forward step, and inside this we are doing different things in order. So the backward is exactly the same with the opposite order. And this backward is responsible for making the model better because it calculates the derivatives and gives the model the knowledge in the optimizer to know which parameters contributed more or less to improve the output and the learning. Otherwise, we are not to take a note of them. So this is the basic how a model works, and definitely we are going to touch one by one of these attentions and networks and all these steps together in order to have a better overview of how this code works. But the basic idea is that based on the selection of the attention and the network, the block takes this code and uses it for the steps in order to make your model work. So practically, this is the high level of this repository. And at the final thing that you can see, you can take it and run it as many times you like. Thank you.